Hello, everybody. My name is Angelina.
Hi, my name is Victoria, and today we will be showing you our project on planetary orbit calculator. Um, so basically, our project is a mixture between programming and astrophysics. We both took interest in this because we took a C++ programming class last semester, so that is the language we will be using in our menu-driven program. So the topic of the program will be orbital mechanics because we took a specific interest to it and wanted to dig deeper into the science behind it.
Amazing. We're separating this presentation into two parts. The first part being on programming. As Victoria mentioned, we did this code in C++, and this code was written on a website compiler for the reason of making it really easy for us to collaborate and to share the code. So the face of this program is a menu-driven system, and this allows the user to perform multiple calculations at once and to exit the program whenever they want. This screenshot below is exactly what the user sees as soon as they start the program. Okay, so it's a modular system, and the way we sectioned it off was putting each calculation or each physics law as its own function. So over here in the screenshot on my right, or on the right of your screen, you can see the function for Kepler's third law. The void, which is written in yellow, that tells the code that this function will not return any value. It's not sending any information to the code. It's simply going to make a calculation and output it. Now, we decided to title each of the function very simply Kepler's third law. And then for Kepler's first law, we titled it Kepler's first law, just to make it really easy for us to organize this code. Okay, now on to Kepler's third law. If we could deep dive into how this function works. So the user is going to input the average distance in AU. It was important that throughout the program, it was specified in which units the user must input. So that's really made clear the units that the person must input. Now, if we talk about memory and how it works, when a person inputs a certain value, it'll get stored in the ARM. And the ARM is the short-term memory of a computer, and it gets stored in the computer's CPU. And the reason why it goes into the short-term memory is because we determined on our end as a coder, we determined that all of our variables would be integers. And integers are very simple type of integers used in coding. And they only use 4 bytes in the RAM. It's very simple, basic type of stuff. At the end of this code, it'll output the orbital period in years. And for us to be able to output this value, we need to do a calculation. So on the right of your screen, we could see P equals square root POW, which stands for power, 8,3. So this is the computer's way of understanding the formula. And the only way that we could use the things written in yellow, square root and power, we must include the beginning of our code, CMath and string, which is on the left. So basically, before you go into your code, you need to tell the computer that you're going to be using high-level math, and then it'll almost tell the computer, okay, we're going to be able to use square root and power going into this code. Now, this is what the user will see. Initially, they will input the astronomical unit, the average distance between the sun, which here we put as 3, and then it'll simply output the value in years. And at the end, it'll say, would you like to perform another calculation? Yes or no. And this is, I think, to me, the coolest part about this program is that you could continue doing as many calculations as you want until until you're done with the program. So if you click Y, it'll bring you back to the main menu, and if you click no, then it'll end the program. So the next formula we decided to compute was Kepler's first law. The user must input the semi-major axis and the eccentricity. And the complex part about this code, while the astrophysics part is pretty simple because we went it over in class, the code part is a bit more complex. So as we know, we will need to validate if the eccentricity is between 0 and 1. And we do this using an if statement. And this is what it looks like. So this if statement is, you're going to use the logical OR, which is it's two lines next to each other, just like this. It's an operator that says if it's true, we keep on going, and if it's not, then you stop. So over here, we in the bottom screenshot, you can see that we go if E is less than 0, or those two lines mean or, E is greater than or equal to 1, it will output what we have over here. So in the case that that E is, it follows those conditions, it'll output error ... eccentricity must be between 0 and 1. Let's see what that looks like. So over here, as an example, I put an invalid eccentricity of -1. You can see that next to the first arrow. And below that, in the error output, what the computer will tell the user, it'll say error ... eccentricity must be between 0 and 1. And once again, it'll bring you back to the same question, asking if you want to perform another calculation, if you want to keep going, or you want to finish the program. Now, for Kepler's first law, the user is allowed to choose if they want to calculate the perihelion or aphelion, and they do this by entering 1 or 2. And again, at the end, it'll say if you want to perform another calculation. Now for the last equation, we have the V-visa equation, where the user will input mu, the radius, and the semi-major axis, and then it'll simply output the speed. Just like for Kepler's third law, we use square root, and that's where it was important for us to include CMath. Okay, so there were two main key concepts in the C++ portion of this code. And the first is the do-while loop. So to make things very simple for you to understand, the do-while loop is useful for when you want to repeat something over and over again until the user quits. So if you think about our code, it's that menu-driven system to going, yes, do you want to continue this code or continue do more calculation or no? And so in this screenshot over here, the do is what you want to keep on showing up, and the condition, which you could see is the while, is the why. So if they put something that is not y, then it will stop the whole code. And if you could see why we have a capital Y and a little y, it's in the case that, say, one user will put in a capital Y or a little y, you still want them both. You want the computer to understand both. Now, the next concept that we used was a switch statement. This allowed us to easily organize all of our functions together. So in orange, you could see the three functions that we use: Kepler's third law, the orbital speed, and Kepler's first law. Now, each of these functions are associated with a number. So you can see that the Kepler's third law is associated with number 1, and so on. And the way it works is, as in the last sentence written in green, please enter a number between 1 and 4. If the user enters, say, for example, 2, it'll go and it'll start computing the function associated with the orbital speed. Now, I made a little table to make it easy for you as someone who doesn't necessarily understand coding and is new to the C++ language. So if we start off with a switch statement, the purpose of this in our code is that it chooses which set of instructions you want to run. And our program specifically, it'll pick between the 3 laws, or of course, if you want to exit the program. Now, an everyday analogy would be pressing a number on a vending machine. You get the choice to choose which one you want, just as you got the choice to choose between Kepler's first law, Kepler's third law, and the v-visa equation. Now, the do-while loop is a loop that will repeat until a condition is false. The condition that was false is if you, in our program, is that you said you wanted no, you do not want to continue any more calculations. Yeah, and then an everyday analogy would be that say you're playing a video game, and at the end of your game, it'll say, do you want to play again? Yes or no? Off to Victoria.
Okay, so for the next part, I will be explaining the orbital mechanics part of this project. So on this first slide, we can see the three formulas that we have learned in class. So the two for Kepler's first law, which the first one calculates the perihelion and the second the aphelion. And then we see Kepler's third law, which is for the period, which the period will be calculated in years, and the semi-major axis will be calculated in AU, as Angelina said earlier, which is how we are asking the user to input the value of A. So for the v-visa equation, the reason why we were interested in this equation and what it does is it calculates the orbital speed of the orbiting mass on any point of its elliptical orbit. So the factors that it includes is mu, which is g times m, so the gravitational parameters, and then it uses the semi-major axis and the distance between the orbiting bodies, so the distance per se from Earth to the moon, wherever it is on the elliptical orbit, and that will allow us to calculate the orbital speed. So as explained on the slide, when a planet moves closer to the sun, its velocity increases because the gravitational pull is stronger. So for its energy to stay the same, the speed will increase. And when it moves further away, the gravity weakens, which means that it slows down. So that being said, the mechanical energy is always conserved in an elliptical orbit. So this equation is based off of that, allowing the energy to stay the same. The speed varies. Yes. So as we can see here, the v-visa equation was derived from the mechanical energy equation, which can be seen on the first line of equation. And putting those two definitions of mechanical energy equal, we can see that the mass of the orbiting object is not there, and the reason for that is that it is cancelled out on both sides of the equation, so we just ignore it. And so putting those two equations equal, we can isolate v and then end up with the equation that we see on the last line, which is the v-visa equation that is used to find the orbital speed. So now on to the special cases that can modify the equation. One special case is if the orbit is a circle, then the radius will always be equal to, in this case, in the formula, the semi-major axis, which is A, so A can be replaced by R, meaning that the planet will just move at constant speed since it is constantly the same R, so there will be no change in speed. The second case is if it is an elliptical orbit, then R will vary, as we know, because at the perihelion it is closer to the object, and at aphelion it is further. So R changes, which obviously changes the speed as well. So a third special case is when it is a parabolic orbit. This case is very rare because for this to happen, the mechanical energy has to be equal to 0, which means mechanical energy is exactly equal to kinetic energy, and that is very hard to obtain in our universe. So it's very rare, but it gives that the orbital speed of the object will be equal to its escape speed, meaning because it just passes by. So A will tend towards infinity, meaning that we can just ignore that part in the formula, and the formula will become, as seen, v is equal to square root of 2 mu over the radius. The last case is if the orbit is hyperbolic, which means that the speed will have to exceed the escape speed. So it's when the speed is larger than in the parabolic example. A will become negative, and so that's basically when, for example, comets pass by or other objects as such, so it just passes by and continues its route. So the only difference between these two, like a main difference which will differentiate parabolic and hyperbolic, is that the eccentricity of a parabolic orbit will be equal to 1, and the one of a hyperbolic orbit will be larger than 1. So that is an easy way to differentiate which kind of orbit we're working with. Lastly, this is a quick little bibliography of the sources we have used. We can see a C++ textbook, which helped us to create the code, as well as other more scientific links to websites and different sources that we have used for the formulas. Thank you for watching.
Thank you.
Hello, this is what it would look like if you were to run our code. You would click run. Everything on our left side is our code, so you wouldn't really want to touch that. And then on the right is what the user would see. So right over here we have our menu system, which is 1, 2, 3, or 4. You could choose any of these options. So today we're gonna start with calculating the orbital period. So I'm going to click option 1, and then I simply click enter. Then this shows up. So it says orbital period calculator, Kepler's law. This program calculates the orbital period using Kepler's third law, and it shows the formula, and then it tells you precisely to put your semi-major axis in astronomical units. So I'm just going to say we'll put in 3, and it inputs exactly what my period is. Say I want to perform another calculation, I'll put yes, and then that menu again shows up once again. So I get to choose whatever calculation I want to do. This time I'm going to choose the perihelion or aphelion. Now it's telling me to enter the semi-major axis. Let's say my semi-major axis is 2, and my eccentricity is we'll say 0.4. Why not? Actually, you know what? We're going to do a negative value, an invalid value of negative 0.5. Let's see what happens there. It'll tell me error, so I must restart the calculation. I'm not going to restart it. What I'm going to show you is how to end the code, and that is by clicking N. So at the end over here, it says, would you like to perform another calculation? If you click Y, it'll bring you back to this menu over here, and if you click no, it'll end the code. What does that look like over here once I click N? Thank you for using the planetary orbit calculator, and it is done. Thank you for watching, and that is what our code looks like.